So today we are going to talk about section 2.7 Fourier transform. So the homework problem for these sections are 2, 3, 4, 10, 11, and you are all asked to hand in only number 2, number 10, and number 11, and they are due on April 8th. I will post these problems on Sakai on Canvas under assignment as well. So you should do the homework problem, scan your work, and submit it through the Canvas site. Okay. So what is a Fourier transform? So by definition, Fourier transform is a transform that applying to a function u that is defined on a real line, the whole real line into a real line. And the Fourier transform of u, we will use a variable here would be c, and the definition is the integral is from negative infinity to positive infinity, ux e I c x dx. Now, in this case, this x would be spatial variable, and this c, we usually refer it as the frequency variable. Now, this integral, this is a fact. This integral would be would exist. This is an improper integral. This improper integral would be convergent if this function, the absolute value of this function, is Riemann integrable. Then this exists. And in fact, it not only exists, it has any order of the derivatives. So it's a smooth function. Now let's compare this with what we learned before, the Laplace transform. So for the Laplace transform, let me use a different color for Laplace transform. For the Laplace transform, we we apply it to a u, which is a function defined from 0 to infinity, a real value function. And the Laplace transform of u is, we use the variable s, is the integral from 0 to infinity u t e I e negative st, and the integration is with respect to t. Now, if you compare these two definitions, you know that this term here is a real value. But this term here is complex value. You may recall that this equals to cosine cx plus I sine cx. So one of the difference between the Fourier transform and the Laplace transform is that let me go back to the so there are two differences at least. Between these two operators is that first, this function here is actually a complex value function, where this function here is real value. So that is one of the difference. Another difference is that the Fourier transform and the Laplace transform, they define on different function space on different function space. For example, f the Fourier transform is defined on function u actually must be defined from negative infinity to positive infinity. It could be real value or complex value, but in this class we always assume it's real value. But the Laplace operator, it applying to a u actually need only to define on the positive real axis. Now this actually is not only the definition of the function they are defined, but actually they also have defined on different function space. For example, if I let u is a function that actually is 1 when x is greater than 1, or you can use a t as a variable, and when x is less than 0, I mean 0 here, and then this is 0, then you can define the Laplace transform of this function. So I now switch the variable to s, so to be consistent with what we had before. So then this would be, the integral would be from 0 to infinity, because the function u is 1 when t is greater than 0. So the integral, what you have here is 1 e negative s t d t. So the antiderivative of this is negative 1 over s e negative s t, where t run from 0 to infinity. You know that when s is positive, then this term would go to 0, as this term would go to 0 at negative infinity when t is a positive infinity. So the exponent is negative infinity. So therefore, this would equal to 1 over s when s is greater than 0. So that we can compute the Laplace transform of this function. Actually, in this case, we only need that the function is defined on x greater than or t greater than 0. However, if you want to compute the Fourier transform of this, let's see what happened. The Fourier transform, now I switch the variable, it becomes x and c now. And then this would be the integral from negative infinity to positive infinity of u x e I c x dx. Now, because the function is 0 from negative is 0 when from negative infinity to 0, so the integral actually happen only from 0 to infinity u ux ux is 1, so actually ux is 1 when x is from 0 to infinity. So you have this ei cx dx. Now the antiderivative is I c e I c x. Now x run from 0 to infinity. Now remember, these are just cosine cx plus I sine cx. So this term, when x goes to infinity, this cosine and sine, the limit would not exist. They are oscillating between -1 and +1. So therefore, this integral, this improper integral does not converge. So and then the Fourier transform does not exist. So then, therefore, for this function, u here, the Laplace transform exists, but the Fourier transform does not exist. So that is what I meant by that. These two transform defined on different function spaces. Now, for us to define the to give a function space for the Fourier transform, that it turns out that the space of function we should consider naturally, I mean, if you get into higher level of mathematics, is what a class that is by let me have a smaller slide, by the Schwartz class. Okay, what is a Schwartz class of functions? So okay, Schwartz was a French mathematician, and he was awarded a Fields Medal because of his work in this area. So a Schwartz class is a class of function usually we denote by a script x. That is what we call as a rapidly decreasing function. Now those are the function. Those are the smooth functions. So it has a smooth means that it has a derivative of any order, and the derivative are continuous. A smooth function whose derivatives, any order of derivatives goes to 0 faster than any power, any negative power. Okay, so this is kind of like a descriptive definition, but you can make it precise. So let me write the precise definition. Is the set of OU that is C infinity. C infinity just means that any order of the partial derivative, any order of partial derivative exists and are continuous. So these are functions that they define on an Euclidean space, and then the any order of derivative. So this we will just think about it as one variable. So any order of derivative or partial derivative, if you have more than one variable, is less than some constant m times the norm of x to any power of n for any k and m. Those are natural numbers or non-negative integers, and then there exists some m constant. Okay, so this is by definition the Schwartz class. I don't want to. These are actually the kind of function space you study when you study distribution theory, which in this class we are not going to focus on. All right. So, but I would like to say this as a proposition or a theorem. So this theorem tells us that it has several effects. F actually is a map from x to x, from the Schwartz class to a function from Schwartz class to another function in the Schwartz class, and this map actually is one to one and onto, and it is also a linear map. So linear means that F mean map C1 U1 plus C2 U2 equals to C1 F U1 plus C2 F U2. So this linear. A linear you can just this just follow directly from definition. However, we are not going to prove that this is one-to-one and onto. So this we could just accept this as facts. Now, what is useful to us is that the reason that we are learning Fourier transform here is because we want to use Fourier transform to solve a partial differential equation, and the property that are useful to us when we're trying to solve a partial differential equation with the Fourier transform is because of this property about derivatives. So this property actually is quite similar to what we learned for the Laplace transform in the previous section. So the Fourier transform of a derivative of order kth order derivative is actually can be computed by just times I c kth power times the Fourier transform. This is the U hat is another notation for the Fourier. This is another notation for the Fourier transform. SC. For any function u that is in the Schwartz class. For the purpose of this this class, this course, you can always assume that the function in this, at least in this section, are all belong to the Schwartz class. All right. So how do we prove this? Let's see how we prove this. So this actually is just a simple consequence of integration by part. Okay, let's just do the first order derivative. So that this, by definition, this is the integral from negative infinity to positive infinity, and you have u prime x e I x c dx. Now we use integration by part. We think of this, put on this in, and then this would give us u x e I x c minus, and then derivative of this term times u. So let me rewrite it as this derivative of this term. We would have I c come out. Let me erase. We have I c come out, and then this would be negative infinity to positive infinity, and then now we have ux e I x c, and the indigo is with respect to x. Now this is when x is negative infinity and x equals to positive infinity. Now here we use the fact that for this for the function in the Schwartz class, this would ux as x go to positive or negative infinity, this would be 0. So therefore this term is 0. So at the end, what we have here is negative I c, and then this indigo here, u x e I x c dx. Now this term is obviously is the Fourier transform of u. So therefore we put this formula for k equals to 1, for k equals to n, for any arbitrary k, you just use induction principle and or just repeat what is going on with we just repeat it using the repeatedly using the integration by parts. So that is the proof of this. Now, if you recall what we learned in for the Laplace transform, you would know that we also another property that's useful when we're trying to use Laplace transform to solve a differential equation is the convolution property. So let's recall back convolution property. So now here the function uv, remember, is defined from negative infinity to positive infinity, and then the convolution of this function is defined at x is defined, the convolution at x is defined by this formula u. I would let I can still use y or use a tau as my variable. So let me use y here. Okay, so this should be u x minus y and vy dy. Now you may be kind of like curious why this definition of convolution is a little bit different from what we learned when we study the Laplace transform. In the case of Laplace transform, when the function uv is from 0 to infinity to real value function, the way we define the convolution was like this. So in that case, we use the t as our variable, and then this is from 0 to t u t minus tau and v tau d tau. Now the integration is with respect to tau. So you can see that these two, there's a discrepancy between these two definitions. Why is that? But that when you define a new concept, it should be consistent with each other, and actually these two definitions in essence actually are consistent with each other. The reason is like this. Okay, you look at these two. Now, if you think about you extend u to a function that defined on the whole real line, ut is u t when t is greater than 0. When t is less than 0, you extend it to 0 when it's negative. Then these yield a convolution to V at T defined by this definition, actually is the same as is the same as U convolute V tilde T defined by this formula. Why is that? So these two are actually, this is defined through the case when we define the Fourier transform. This is the Laplace transform. This is so why is that? The reason is that when we define when we have in this formula, if so this would be if y is if y are greater than x, then this would be negative. And then this u tilde, this would be 0 on the negative real line. And then we did not have the integral from negative infinity to 0 is because v tilde would be 0 when it is from negative infinity to 0. So these two definitions are actually consistent, but you just need to extend the function in the Laplace transform case to 0 on the negative real axis. So this is something. Okay, so let's go back to the main purpose of the definition of convolution. The main purpose is the same as before. That is that the Fourier transform of convolution of two functions is actually the product of the Fourier transform. The product of the Fourier transform. Now, we also define the inverse Fourier transform. The inverse Fourier transform. So you have u x and then through f, this f, and then you get a u hat c. That's the Fourier transform, and there's also an inverse Fourier transform. And the inverse Fourier transform actually is given by this formula, u hat, and then now it becomes. So this is the integral is 1 over, that should be 1 over 2 pi. And then this is u hat c e I negative x c x, and but the integral here is for c from negative infinity to positive infinity. So that is the inverse Fourier transform. It's kind of like we have the inverse Laplace transform that map the Fourier transform back to the original function. Okay. So, therefore, similarly, we have that the inverse of the Fourier transform of two functions map back to the convolution. So that is just another way to say this theorem. All right. Let's see why is this true? How do we prove this? The fact that the Laplace transform, the Fourier transform of a convolution is the product of the Fourier transform. Okay, so just recall u v this function at t we use x is from negative infinity to positive infinity. This is u x minus y v y dy. Now, then we apply the Fourier transform to these two functions, to the convolution, and this would get us a c. And okay, so this is an integral from negative infinity to positive infinity, and this is u v x e I x c dx. Okay, I applying this formula here into this term. So then this would be negative infinity to positive infinity u x minus y v y dy, and this is e I x c dx. Okay, so then I write this term here as e I x minus y c and times e I y c. So then I have this. I would dx first. Okay, let me have a dy is the integral, right? As an iterative integral, and then I have a change of this vy e I y c dy, and then this is u x minus y e I x minus y c dx. So here, if after we do a substitution, let's say change this to z, and then we see that these actually become this is just the Fourier transform of v, and this is just the Fourier transform of u. So therefore we prove this convolution property. So the key fact is actually the same as in the Laplace transform case. That is that the Fourier transform map a convolution to a product. All right. So now let's when we try to solve a PDE or ODE, a differential equation using Fourier transform, we also need to have a table of Fourier transforms. But here I will just give a few that we are going to use in this class. Table of Fourier transform. So first we have so this is the original function ux, and this is Fourier transform u hat c. For Heaviside function, h is the Heaviside function, a minus absolute value of x. This is Fourier transform is 2c sine a c. Okay, so this function here is what we call as the square pulse function. It is, if you want to draw the graph, is the graph looks like this. You get here from negative a to a, and it is 1 here, and then it is 1 here, and it is 0 here. So that let me change the color so you can see this 1 here and 0 here. That's the okay. All right. There are another one that we know is the Fourier transform is the exponential function. This have absolute value of x, and this is a square plus c square 2a over a square plus c square. And another function we can compute the Fourier transform easily is the Gaussian function. This is the normal distribution function. This is usually referred as Gaussian function, and its Fourier transform is a square root of pi over a e to negative x square over 4a. Okay, so these are the 3 functions that we will use in our homework and in the examples. All right. Let's just use as an example. Let's just compute this, verify some of these. Example 1, part 1. Okay, let's do the square pulse function. So by definition, we have the u had the Fourier transform. So it is 1 between negative a and positive a. So the integral and then elsewhere is 0. So the integral is from negative a to a, and then this is 1 e I x c. The integral is d x. Okay, remember this is this is cosine x c plus I sine x c dx. And then once you do the integration, you will know that this is cosine, because this is an odd function, so therefore this is an odd function. The integral is going to be 0, and therefore you have only this term left, and in this case the integral of this is going to be 1 over c sine x c, where x run from sine from negative a to a. So therefore at the end you get 2 over c sine a c. That is exactly what we have here in the table. That is exactly what we have here in the table. Okay, let's also verify the Gaussian function, the Fourier transform for the Gaussian function. Okay, so now in this case, the Gaussian function is here. So in this case, the Fourier transform is this from negative infinity to positive infinity, e negative a x square. Remember, we also have the term I xc, and then the integral is with respect to x. Okay, so as before, the key point here is to complete the square in the numerator. So let's do the completing the square. Ax square plus I x c is this is let's okay, I factor negative a out, so this I have x square minus I c a x. Okay, then in order to complete the square, I add okay, all right, what is happening to what comes about from my okay, so so I have a, so I have an x square minus I c a x. I add the term I c 2a square, and then I minus the same term back, so become plus a I c 2a square. So this is negative a x minus I c 2a square. I square is negative 1, so and this a square cancel out, so I get 4a in the denominator, and I get c square in the numerator. So therefore, the Fourier transform is this term here. I get it out of the integral sign is actually this c square 4a. And this integral is from negative infinity to positive infinity e negative a x minus I c 2a square d x. Now here we use a substitution, y equals square root of a x minus I c 2a, and then after the substitution, this integral here would becomes e negative c square 4a. Then when x is negative infinity, y will be negative infinity, but I would actually explain this a little bit later. So this would be e negative y square dy, and then we need to have the square root of 1 over a here. Now this term here, we know it equals to square root of pi. So therefore, at the end, we have the formula pi over a e negative c square over 4a. If you go back to look at the formula that we had before, that is exactly the table that we have, that is exactly this formula that we have over here. I actually need to come back to correct this. This variable here should not be x, it should be c. Okay, so let me correct this. It should be c square. Okay. Now, let me explain this little bit subtle thing happen here. So the original integral is actually is on the x-axis. This is going here from negative infinity to positive infinity, so it's on along the x-axis. But when we do the substitution, I let Z actually is not probably not a good idea to use Z. Let me use I'm not use Y. Let's use Z. Okay, I let Z equals to this. This would be negative Z square, and this would be DZ. Okay, now the indigo. When I do the substitution, Z actually is not the same real line. It's not here. It has an imaginary part. The imaginary part is C over 2A. Actually, when we in this indigo here, we are actually Z actually runs on this line here. Now. It turns out that these two indigo are running along this real line here, and this line here, these two indigo are the same, and that actually you would have to refer back to your what you learn in complex variable. The reason is because of this function is an entire function, and it has decay properties, and it has no singularity between these two real lines. So, but I'm not going to get into this. You can just assume that this what we did here is legitimate. So, okay, I would just stop here for the time being. Then I will have a break, and I will come back for the next second part of today's lecture.